Let's take a look at using significant digits in calculations. Be able to determine how many significant digits an answer to a calculation should have and round that answer to the proper digits. The uncertainty that you have in each of your measurements carries through the calculations you do with those measurements. And there's two fairly straightforward rules for you to remember. For multiplication and division, it's based on the number of significant digits in your measurements. So you count the number of significant digits in the measurements, and then you are going to use the fewest digits in your answer. A lot of times students get used to this very quickly. We do a lot of multiplication and division in our chemistry calculations. But every so often we do have to add or subtract something, and it's important to remember that addition and subtraction have a different rule. It is based on the place value of the significant digits, not the number of digits in each measurement. And in each case, we are going to choose the least certain in order to come up with the significant digits of the calculation, because if you think of the saying that a chain is only as strong as its weakest link, we can only be as certain of the results of a calculation as we are of the least certain measurement that goes into those calculations. Let's try a few of these multiplication and division. So here we have a measurement, a density value that is known to 3 significant digits, and a volume that is known to 2 significant digits. And when we multiply this, that means that our answer is going to have 2 significant digits, the smallest number of significant digits that we can. When I calculate this, the milliliters cancel because we have 1 in the numerator and 1 in the denominator, and the answer will be in grams. And my calculator gives me this number, 30.52, which has 4 significant digits. We have to round this down to 2 significant digits. So 1, 2, we want to round it to the ones place. The 5 is large, so we are going to bump this up to a 1 and call this 31 grams. Here we have a measurement with 4 significant digits and a density that is known to 3 significant digits. And so our answer is going to need to have 3 significant digits. The result of this calculation is in milliliters, and my calculator gives me quite a number of digits. It fills up the screen, but I know I only want 3 significant digits in my answer, 1, 2, 3. The 2 is small, so we are not going to bump up the 5. This is going to be 92.5 milliliters. Here we have a value with 5 significant digits being divided by a value that only has 1 significant digit. So our answer is only going to be able to have 1 significant digit. Again, my calculator gives me quite a number of digits. When I round this down to 1 significant digit, I get 0.1 grams per milliliter. And this last one has a number with 4 significant digits multiplied by a number with 5 significant digits. We are going to want to have 4 significant digits in our answer. This time my calculator just shows the answer 2 on the screen, which only has 1 significant digit. And so we're going to add more significant digits in this case, because these measurements are fairly precise. So we're going to show that by writing this as 2.000 centimeters squared. So for this addition and subtraction problem, we are going to count the significant digits just so that we can tell where the last significant digit is. The number of significant digits actually doesn't matter. So this first measurement has 5 significant digits, and that is important just to show us that this 5th significant digit is where the uncertainty is. And this one has 3 significant digits, and that just shows us where the last significant digit is. We're going to keep the uncertainty in the leftmost place value here. Students sometimes find this a challenge because the best way to do this is to line these up. When I put this into my calculator, I get the answer 66. Let's take a look at how certain we are of that value. Our first term has the uncertainty 3 past the decimal, and our second term has the uncertainty 3 past the decimal. So our uncertainty is really 3 past the decimal. This answer is known to plus or minus 0.001 grams. Let's go ahead and show that by adding in some zeros here. It's best to write this answer as 66.000 grams to show that we've measured these masses with a balance that goes 3 past the decimal, and so that's how certain we are of the result. For this second problem here, we have two lengths that we're adding together, 7,300 meters and 5,160 meters. And the calculator tells me it's 12,460 meters. This first measurement has two significant digits, and so the uncertainty is in this second digit, the 300 place. It's plus or minus 100 meters. The second measurement has uncertainty at this third and final significant digit. There are three significant digits here. And so this is where the uncertainty is. And in this case, we have uncertainty in two different places in our answer. And that is not something that we can have. The last significant digit that we show is supposed to be our uncertain digit. And so we need to choose the leftmost of these places, the hundreds place, because if we have uncertainty in the hundreds place, there's no sense reporting the tens place. If this number is plus or minus 100, there's no sense saying that this 60 is known. So we need to round it to the hundreds place. The 6 is large, so we're going to change this 4 to a 5 and report this as 12,500 meters, showing that the uncertainty is in the hundreds place. For this next problem, we have a volume of 850 milliliters, and we are subtracting 1.33 milliliters from that, and the calculator tells me it's 848.67 milliliters. This first measurement, the way it's reported, is showing two significant digits. The uncertainty is in the tens place. This is plus or minus 10 milliliters. This second measurement is known to past the decimal, the hundredths place, because it has three significant digits, and the last significant digit is this 3 at the end. So our answer has uncertainty both in the tens place and in the hundredths place. We have to choose the leftmost value here. If we don't know this value to plus or minus 10, there's no sense reporting these other digits. The 8 is large, so we are going to bump this 4 up to a 5 and report this as 850 milliliters. So some people are confused because it looks like it didn't make a difference, but if you think about it, if you don't know the volume you have to plus or minus 10 milliliters, if this could be 860 milliliters or 840 milliliters, then 1.33 milliliters actually doesn't make a difference in how well you know what volume you have. And for this last one, I found a little space in this corner to add these two lengths, 0.02500 centimeters, a measurement with 4 significant digits that is known to 5 places past the decimal, adding that to a length of 7.82 centimeters, which has 3 significant digits and is known to the hundredths place, 2 past the decimal. Our answer, therefore, has uncertainty in 2 different place values, 2 past the decimal and 5 past the decimal. So we are going to round it to the leftmost space, 2 past the decimal. The 5 is large, so we're going to bump up the 4 and this should be reported as 7.85 centimeters, known 2 past the decimal. This one is known to the tens place. I wanted to point out a couple of examples dealing with exact numbers and how the significant digits apply in those calculations. So here we have a situation where you have 6.23 grams of salt and you want to divide it evenly into 4 beakers and figure out how much salt will end up in each beaker. When I type this into my calculator, I get 1.5575 grams of salt per beaker. Let's look at the significant digits. This measurement of the mass of the salt is known to 3 significant digits. So this 3 is uncertain. We have plus or minus 0.01 grams of salt. Beakers are a counted item. So we have counted 4 beakers. This is not plus or minus 1 beaker, and it's not plus or minus 0.1 beakers. This is an exact number. If the last digit has the uncertainty, we can never really have a last digit. We can express this as 4.00000 onto infinity beakers because we don't have any uncertainty at all in the number of beakers. So an exact number has infinite number of significant digits. Here's the infinity sign if you want to express it that way. So our answer should have the least or the fewest number of significant digits. So comparing 3 and infinity, 3 is a smaller number. So our answer should have 3 significant digits. We're going to round it down to this third significant digit here. And since the 7 is large, we're going to bump that up and we will say that we can get about 1.56 grams of salt in each beaker. A lot of times this will come up when you have a relationship that is exact. Here we have the relationship between inches and centimeters, and that is a defined relationship. We can also write that 1 inch is 2.540000 centimeters. We could keep going as long as we want because we never run into an uncertain digit. When we do this multiplication, our calculator gives us an answer of 65.71742 centimeters. Our measurement has 5 significant digits. This exact relationship has an infinite number of significant digits. So we want something with 5 significant digits. 1, 2, 3, 4, 5. The 4 is not large enough to bump up the 7. So we can report this as 65.717 centimeters. Not every relationship is exact. The relationship between kilograms and pounds is a lot of times abbreviated to something that's manageable, 3 significant digits. So if we are using this as our conversion factor has 3 significant digits, not an infinite number of significant digits. If you look at the conversion factor up in a more precise reference, you'll find a lot more digits. This is good enough for a conversion factor to use when you have a measurement that only has a few significant digits. For example, this measurement has 2 significant digits, so using the conversion factor that only has 3 significant digits is good enough because we have this for what the calculator gave us, and we are changing it to something that has 2 significant digits. So if we had used a conversion factor with a lot more digits, we still would have to round it down to 2 significant digits and get the same answer. If you have a more precise measurement, here we have one with 6 significant digits. Now if we use this conversion factor, we're actually limited by this conversion factor. It only has 3 significant digits. And so we can't keep the entire answer the calculator gives us. We're going to have to go down to 3 significant digits. So that's probably not the best thing to do. It would be better to get more of these digits from the conversion factor, maybe use this one. So if we have 6 significant digits in the measurement, we can use this conversion factor with 8 significant digits, and then our calculator gives us this number, and we can round it down to 6 significant digits here, getting a more precise answer, which corresponds to the more precise measurement that we're trying to convert. Let's try a couple of multi-step calculations. A lot of times in the course, we are going to have a series of multiplying and dividing to do. And this one is pretty straightforward because multiplying and dividing both go by the number of significant digits. So all we have to do here is figure out that in the measurements we have 4 significant digits, 4 significant digits, and 3 significant digits. And so our calculator gives us this amount of digits, and we want to change this to 3 significant digits because that is the smallest number here. So we want to round it to the ones place, and we end up bumping it up to a 6 because the 9 is large. And so we get an answer with 3 significant digits. When we have a problem that combines adding or subtracting with multiplying or dividing, it's good to keep track of where your significant digits are. Keep all the digits until the end, but keep track of where the significant digits are after each step so that you know where to round the final answer. So the first thing we do here is add. We're going to add 4.27 grams, which is known 2 past the decimal, to 0.863 grams, which is known 3 past the decimal. We come out with an answer that has uncertainty both 2 places and 3 places past the decimal. And so our uncertainty has to be 2 places past the decimal. Instead of rounding it off at this step, we can just keep track of where that uncertainty is, either by underlining, or sometimes you'll see the 3 significant digits written out like this, and then any extra digits written as a subscript. With some of the equation editors, it's hard to show underlining, but it's easier to show subscripts. So you might see it written like this. However it's written, we are now doing a division problem. Our numerator has 3 significant digits, even though we kept a 4th digit here. And our denominator has 4 significant digits. When we do this division, this is what our calculator gives us. And we should go down to 3 significant digits because that is fewer. So 1, 2, 3. We should round this to 0.415 grams per milliliter. Let's do one more example where we're dividing first and then adding. For this division, we have 4 significant digits in the numerator, 3 significant digits in the denominator. This is what our calculator gives us, but we know that we should only have 3 significant digits. So I'm going to go ahead and underline that and put a note that this has 3 significant digits. And that is where the uncertainty is. Now we'll go ahead and do our adding. We'll add 4.3472 meters per second, noting that our uncertain digit is here, the 3rd significant digit. And then we're adding that to 18.1 meters per second, which has uncertainty at the 1 past the decimal. Our result has uncertainty both 1 and 2 places past the decimal. And so we have to go with the position on the left. So our uncertainty in this result is 1 past the decimal. If we were doing more calculations on this, we could just carry it forward with the underlining, but since this is the final result that we're reporting, we'll go ahead and round it off and report 22.4 meters per second.